Hi, welcome back to the series playlist on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. Alright, in this video we're going to cover the root test, which is really the final series test that we generally cover before we get to the all-important power series. And so this test, the root test, is related to the ratio test. It doesn't look the same, but it actually boils down to the same three conditions that we use to draw a conclusion about the series. Alright, so here we have just a general series, n equals 1 to infinity, and we have some function of n as we normally have, right? And generally when we know to use the root test, it's when we have either the entire argument of the series raised to some power, as we have in example 2, notice we've got this 3n plus 1 over 4 minus 2n, and notice it's all raised to the 2n power. That's a dead giveaway to use the root test. In fact, generally, most professors on a test will put something like this, where you have the entire argument in brackets or parentheses and the whole thing's raised to a power. But another case where you can use it is, notice here in example 1, I've got individual numerator and denominator each raised to a different power. Okay? So generally, when everything's raised to a power, either all together as in the second one down here or individually, that's a good clue to use the root test. And generally speaking, we are going to use the ratio test, which we covered previously when we've got factorials, and we're not usually going to use the root test when we have those. Okay? So what you do is you take the entire argument of the series and you evaluate it as a limit as n goes to infinity. So we usually call that L, just like we did in the ratio test. L is the limit as n goes to infinity of our function f of n raised to the an power. But what we do in the root test is we raise this whole thing, and here's the key, to the 1 over n power. So whatever the entire argument here is of the series, we take the limit as n goes to infinity and raise it to the 1 over n power. Sometimes this root test is called the nth root test because we're raising it to the 1 over n power. And generally speaking, that raising everything to the 1 over n should cancel the n that was already there, and so you're just left with some power. Okay? And then we say that if the limit is less than 1, the series converges absolutely. We don't have to worry about conditional convergence here, just as in the case of the ratio test. If L is greater than 1, the series diverges. And if L is equal to 1, the test is inconclusive and we're forced to use something else. Okay, let's look at two examples of this, and hopefully you'll see that the root test is actually not all that bad. Alright, here's our first series. We've got a series from n equals 4 to infinity. We have negative 5 raised to the 1 plus 2n power, divided by 2 raised to the 5n minus 3 power. So what are we going to do? Well, we're going to say the limit of this L is equal to, the limit as n goes to infinity, and notice what we did. We just took this entire argument and put it in here, put some brackets around it, and raise it to the 1 over n power. Now in this case, what happens is, we just distribute this 1 over n to each of these individual exponents, right? So 1 times 1 over n becomes 1 over n. 2n times 1 over n becomes plus 2. Okay? We do the same thing in the denominator. 5n times 1 over n becomes just 5, and minus 3 times 1 over n becomes minus 3 over n. And actually, we can now simply evaluate this limit, because if we plug in infinity, basically, for each of these n's, then these fractions go to 0. And so all I'm left with is negative 5 to the second power, because again, the 1 over infinity goes away, that's just 0. And then in the denominator, if I plug in infinity for this n, 3 over infinity is basically 0. So this is just 2 to the 5th power. Okay? And so this becomes negative 5 squared, and that's 25, and 2 to the 5th, which is 32. Now, one thing which I haven't indicated here, it's rarely crops up, but it is somewhat important if you have a negative sign out in front. You are taking the absolute value of all of this just as you were in the ratio test. So if this had come out for whatever reason, negative 25 over 32, you just take the positive value of that, so 25 over 32. Okay? And we notice that this limit is less than 1, so therefore this series converges absolutely. And so we might say converges absolutely by the root test. Alright? So there's our first example. Let's now look at one more example down here. We have a series from n equals 1 to infinity. And now we've got this whole thing raised to the power. So that's a dead giveaway that we're to use the root test. So we have 3n plus 1 over 4 minus 2n, all raised to the 2n power. So our limit L is, the limit as n goes to infinity. And again, I just took this whole thing, this whole argument of the series, and put it here, but I have to raise it to the 1 over n power. So notice I just took the 2n that was already there and divided by n. That's the same thing as raising everything to the 1 over n power. And again, nicely, these n's cancel. And so I'm left with the limit as n goes to infinity of 3n plus 1 over 4 minus 2n, and that's raised to the second power because the n's canceled out. All right? Now, there's a number of different ways that you could evaluate this limit right here. Notice that if we plug in infinity, we would have basically infinity divided by negative infinity, which is indeterminate form. So we could use L'Hopital's rule to take the derivative of the top and bottom. And inside the parentheses, at least, that would give 3 over negative 2. Or we could just recognize that the highest power of both of these is the same, and so we just take the coefficient of those n's. So it'd be 3 over minus 2. Basically, after you use the 1 over n right here, and right here, any root test basically boils down to evaluating a limit by whatever means necessary. So you could use L'Hopital's rule if you'd like here, and we get 3 over negative 2. Again, it's all raised to the 2 power, so it's squared. So 3 squared is 9, negative 2 squared is 4, and so we get 9 over 4. Now notice in this case, 9 over 4 is greater than 1. Therefore, this second series diverges by the root test. All right? Now, if we had a third example, which I don't have here, and we did the root test and we got L equals 1, then the root test cannot be used to determine convergence or divergence. We would therefore be forced to use a different test, and probably not the ratio test. We'd have to use something back from what we learned before. So maybe integral test, alternating series test, different things that we saw before. Okay. One thing I will mention is these two tests, if you wanted to, particularly this one up here, you might be able to solve these with the ratio test. So some of these, and it might take some work and it might be a little bit difficult, but some of these you might be able to solve with the ratio test. I haven't actually worked those out. It's just that when you've got these powers like this, it makes it much easier to solve using the root test. All right? So hopefully this video made a little bit of sense and gave you a handle on the root test. It's a fairly straightforward test. All right? Please make sure to like this video and subscribe to the channel for future videos and notifications. We may do a little bit more with the root test in a separate video, some more examples, and after that we're going to move into the all-important power series. Thank you for watching.